an action that was quite elegant. And then, after doing a little work, writing what ds is, was equal to minus mc integral from some parameter minus eta mu nu dx mu d tau dx nu d tau d tau. We wrote it in this way, which was a way to introduce a parameter to describe how this particle is moving, and then with the help of a parameter, writing the action in a slightly more explicit way that you can just calculate with it. An important fact about this parameter is that it's not really needed. That is, if somebody would have given you this motion of a particle, here is x, here is ct, and this particle is moving some way, you could have just come here and cut this in pieces and calculate what is the ds for each one and add them up. That's the meaning of this integral. Nevertheless, we decided to parameterize this thing with a parameter tau that is totally and completely arbitrary, except that, you know, as a particle moves, the parameters should be changing, but that's what parameters are supposed to do. But apart from that, the spacing, if these are equal tau spacing now, they could just look different at any stage. You could choose whatever you want, and you can help yourself with this parameter to calculate this integral. Now, the parameter choice is completely arbitrary. And we say that we look at this formula and say, this is reparameterization invariant. By that, we mean that if you would have decided to use a different parameter, tau prime, which is some function of tau, you could use the chain rule, and you say, well, here I have the chain rule between tau and tau prime, and here the same. But at the end of the day, the effect of the chain rule here and the chain rule there and the chain rule here cancel, because there's like a square root of d tau, square root of d tau, and a square root of d, and a d tau in the numerator here. So you look at this and you say, oh, there's d tau, d tau, d tau. They really cancel. This is manifestly reparameterization invariant, which is to mean that if you do those transformations, you would find mc tau I prime, tau f prime, square root of minus eta mu nu, dx mu d tau prime, dx nu d tau prime. So you can calculate it using any parameterization. That's the bottom line. And that's very nice, actually. So in fact, when we try to vary this action and find equations of motion, we vary it with the help of a parameterization. It's a lot easier because you have to vary the motion. You have to vary x. Well, so you have to parameterize it with something. So delta x mu of t is the thing that is being varied as you try to find the equation of motion. Now, I think I want to do that equation of motion. It's I think it's pretty and it's sort of interesting. So I'll just do it, even though it's going to cost us a little time. So delta s is equal to minus mc p delta of ds. And the reason I want to do it is because it's easy to go into pretty hard calculations here unless you're very careful. And I want to show you how to be careful about this. Now, the thing you must remember is what we wrote before, that ds squared is minus eta mu nu dx mu d tau dx nu d tau squared. We had that before. It came from basically ds squared equal minus eta mu nu dx mu dx nu. So this thing for a particle that is doing physical motion is always positive. The way we defined the ds squared was, remember, minus ds squared is equal to minus dt squared plus all these things. So for a particle that is static or is moving very slowly, ds squared is dt squared is positive. So this is really equal to what we call ds squared in this case. So you have ds squared is equal to this. And that's the beginning point where you want to go. Because here you have ds, which is the square root of this ds squared. So we vary this one. So we say 2 ds delta of ds. And by varying this, as opposed to varying this directly, you avoid writing thousands of square roots, which is a pain in the neck. So now we have this, and now I have to vary this thing in the right-hand side. So let me just write it. Delta of minus eta mu nu dx mu d tau dx nu d tau squared. Now, when you want to vary that thing, you go here and say, well, I have to vary the eta that doesn't vary, it's a constant. The d tau is not a thing that you have to vary. You have to vary the x's. That's the only thing you vary. But you have 2 of them, and this is symmetric. So you get a factor of 2. Minus 2 eta mu nu delta dx mu d tau dx nu d tau squared. And now you do 2 things. You cancel the 2's, several things. Cancel the 2's. The ds, you're going to move to the other side. And you remember that the variation of dd tau of x is the dd tau of delta of x. So from all this, we obtain now that delta of ds is minus eta mu nu dd tau of delta x mu. So far, so good. I've canceled the 2's, the eta, the ddt. The dd tau has gone here. And look, we want to divide by ds. So I will put the dx nu ds and just one d tau left. So you'll have dx nu ds and just a d tau. Now, I can use the eta to lower this index. So now it has become minus dd tau of delta x mu dx mu ds d tau. And this is pretty neat. You know, we've avoided a lot of potential ways to make this calculation very difficult. Well, there's the mc, so let me just do the whole thing. Delta of minus mc ds by multiplying by minus mc. So this thing now becomes a plus, and I have dd tau of delta x mu mc dx mu ds d tau. And once you do that, you recognize that this is precisely what we used to call the relativistic momentum. So the thing has become really simple. dd tau delta x mu p mu d tau. So we can go now back to the action and say, well, delta S is this variation, this integral from tau I to tau final of dd tau, and this whole thing in here, which is dd tau delta x mu times p mu. Whole variation has become this. To make it even better, we integrate by parts. So we write this as integral from, well, we don't even integrate by parts, but we'll write it as dd tau of delta x mu p mu minus delta x mu dd tau of p mu d tau. So at the end of the day, we get delta x mu p mu from tau final to tau initial minus the integral of over d tau of delta x mu times dp mu d tau. This is basically the key result. So I will write it here as delta S. And it's a result that is useful for other applications. So let me continue. As we have been saying throughout, this time equal initial and time final, we don't have to worry about. These are things that don't impose conditions. They're initial conditions and final conditions. So the equation of motion is just dp mu d tau equals 0. And this is the same as dd tau of p mu is mc dx mu ds is equal to 0. It's a funny looking equation. P mu with respect to tau being 0 means just P mu is a constant on the world line. This is, you see, this example is physically very simple. What you're learning here is manipulating Lorentz invariant quantities and understanding their meaning. And in relativity, this calculation, this is the way you should really vary these things to get the geodesic equation in relativity. And it's a very efficient way of doing it. I recommend trying to do that as well. What's happening is really very physical. dp mu d tau being 0 is that p mu is constant along the world line. You knew that, of course. Here it looks a little more interesting. dd tau dx mu ds is equal to 0. There's two ways you can do this. This ds is not an arbitrary parameter. It's the proper time along the world line. And dd tau is an arbitrary parameter. So you could even choose dd tau to be s. And that's what sometimes people do in general relativity to simplify things. And this implies the second x mu, the s squared is equal to 0. You can choose tau equal s. It's a choice, your choice. You cannot choose s to be tau. The equation dd tau of x mu equals 0 is false. It's not true. This is the true equation. This is not true. For an arbitrary parameter, the second derivative of the position with an arbitrary parameter is not 0. You can make it anything you want. So it's an interesting thing. The reason this formula is very useful is that, as I mentioned last time, if you have a particle coupled to an electromagnetic field, the thing that you have to add is Q over C, integral over the path of the potential in this way. And with those two terms, you will find, if you vary now, delta S equals 0, you'll get this formula, dp mu ds equal Q over C F mu nu dx nu ds, which is the Lorentz force law. And that's a very neat calculation, of course, because this time you have to vary this thing and you have to vary that. And you need to keep track of what you get from this, which is this. So this part is essential to get the right signs, the right correlation between these two terms. And varying this to get this is also a little non-trivial, but it's easier than this variation. It's a very nice problem to do this variation. It's something you should do, although it's not being assigned, or I don't think it's even in the tutorials. But it's something we all should do. So with this, I finished the particle, and we're going to begin with a string. So any questions related to this particle or anything so far today? Yes?
Was your key why this is it the same as the geodesic equation?
This is not quite the geodesic equation in general relativity. And the difference is that there's more things to vary in general relativity. So in general relativity, there's just one little difference there, is that ds squared is not minus eta mu nu dx mu dx nu, but you put here g mu nu of x. So in addition of varying these guys that we varied there, and we did it in a very efficient way, but you should make sure you do it in a similar way, you now have to vary the metric as well. So there's extra terms, and those form the geodesic equation. So the extra terms with Christoffel symbols and that. It's a very neat exercise as well. It's the last problem in chapter 5 of the book. You can try doing it. It's a good review of general relativity. Other questions? Yes?
Can we push this action into the limit of massless particles?
No. This action can't be pushed into the limit of massless particles. For massless particles, you need to write actions that are a little different with things called einbeins and little things. But happily, this kind of action is the action we need for the string, which is a relativistic, in a sense, people call it the massless relativistic string. So this is all we really need at this moment. But if you want to do massless particles as a mechanics, you do need to do the things different. More questions? And more questions. So ready to do strings. That's what we're here for. Okay, so it begins not terribly differently. So we try now to do strings. And we've used for the particle the integral of the proper time was sort of the invariant length along the trajectory. So the thing we're going to try to use for the string is that the string will trace a surface, and therefore let's try to use the invariant area of that surface as the action. And that will turn out to work out right. Now, doing the invariant area, here there's a funny thing. This is the invariant length of this part, of this trajectory of the particle, but it's the invariant length in space-time. So we had the eta and things. So we're going to have to find the invariant surface in space-time, which is not surface as you know it. Surface as you know it is the surface of this page or the surface of this blackboard, a surface in space. But the string in space, the string is just a line. As it involves in time, it traces a surface in space-time. That is the surface you're trying to compute the area. There's another surface associated to the string that should not be confused with the surface in space-time. If you have a string in this room and it would be moving, it would, and imagine it leaves a wake as it moves, it traces a surface in this room. That's not the surface in space-time, it's a real surface. It's a composite of the string at various times, and it's a real surface. It's a space surface. The area of that surface is not relevant for the string. The area that is relevant is the area in the space-time. So we'll have to do it with a little care. So the way we're going to do it first is let's just try to write areas in space to begin with. Once we get that right, which will take us a few minutes, then we'll write areas in space-time, and we'll figure out that there's a bit of a potential problem, but at the end of the day, nothing goes wrong. Okay? So we begin as surfaces in space. So I'm going to try to use the area and begin with surfaces in space. So a surface, just like a line is parameterized, a line in space would be parameterized by x of some parameter psi. A surface in space is parameterized by two things, two parameters. Let's call them sigma 1 and sigma 2. And you have these two parameters. And then you have maps from this to space. So x of sigma 1 and sigma 2. Sigma 1 and sigma 2 is parameter space. It's a mathematical and physical auxiliary space. For any point psi 1 and psi 2, you have a function that moves you into space. So let me draw it maybe a little better. I draw some axis here, and then this maps into some surface in space, x1, x2, x3. And this is the vector that tells you where you are in this surface. The first thing you need to know to write the area functional is how to compute the area of this surface using a parameterization. So you take a little square here, or a little rectangle of sides d psi 1 and d psi 2. And let's try to calculate the area of the image here. So this little square is going to appear here as some sort of parallelogram, presumably. And we want to calculate the area of that little thing using d psi 1, d psi 2. So how do we do that? We imagine that d psi 1, this is the little parallelogram. I'll write it like that here. This I'll call dv1, the vector v1. This is the vector v2. So the vector dv1 is the x vector with respect to psi 1 times d psi 1. Try to imagine why this is so. You know, if you move a little in psi 1, how much do you move in space? Well, that's what we mean by moving in this direction. The vector dv1 is what you end up moving in space when you move in the parameters by psi 1. So how much is it? Is the rate of change of x with respect to that parameter times this thing. And what is dv2? Well, it's dx, d psi2, d psi2. So far, we're just writing this. Now, what is the area of this parallelogram that's infinitesimal parallelogram? The area, in fact, is the magnitude of dv1, the vector v1, cross dv2. That's a formula that you probably know, that a little parallelogram, the cross product gives you the area of it, and the magnitude is this. So better to write the area squared as dv1 cross dv2 dotted with dv1 cross dv2. So the square is that you have the norm here, but to just get the norm in an easy way, we'll just square and do this. Now, you may also remember from vector calculus that if you have A cross B dot A cross B, doing a little bit of work, this is equal to A squared B squared minus A dot B squared. So here we get, this is dv1 squared, dv2 squared minus dv1, dv2 dotted into each other squared. So finally, we can write the area, and I'll write the square root. Oops. And what is dv1 squared? I would have this dv1 there, so it would be dx, d psi 1, dx, d psi 1. And now I have times d psi 1, d psi 1, and I will take that into the square, out of the square root, so you have a d psi 1. And here you'll have dx, d psi 2, dx, d psi 2 for dv2 squared, that's a dot product, and the d psi 2 there, out. And then minus the dot product of these two things with each other, dx, d psi 1, dx vector d psi 2 squared. Looks pretty messy. There's no question about it. It's just somewhat messy, this thing. So we want to do it better and recognize, a few things. Why is this formula unsatisfactory? You look at it and you don't get a good feeling, a happy feeling. It's just a little messy. Moreover, but that's still not concrete. The thing that is a little unclear about this formula is this property that we had there at the top of the blackboard. We said this is reparameterization invariant over there. So here, this parameters psi1 and psi2 should be irrelevant. So I should be able to show that if I change psi1 and psi2 to some psi1 tilde that depends on psi1, psi2, and psi2 tilde that depends on psi1, psi2, this sort of thing just all transforms nicely. And if you look at it, it's very messy because of the chain rule is complicated. It would be a long calculation to check that this is correct. So what we want is a way to pretty much see it. So for that, we have to think a little more about what we call a metric on the surface. So this is a very simple idea. If you have a space and you have a surface in it, if you have a metric on your space, you know how to measure distances on your space, you know how to measure distances on the surface as well. Because 2 points on the surface are points in space. So you know the distance between them. So you know how to measure things on the surface. Now, the metric in three-dimensional space is a 3x3 matrix. If you have a surface here, it would be the metric, the induced metric, would be a 2x2 matrix because the surface is two-dimensional. So the interesting thing is somehow how a 3x3 metric gives rise to a 2x2 matrix. So this is actually sort of implicit in our notation, as we see now. Suppose you have a vector dx on the surface. So dx on the surface is dx d psi times d psi I. You think of this vector on the surface as the result of some variation over the parameters. So in here, I must sum over the two parameters because this is an arbitrary vector. That's why I put an I here. So this runs over 1 and 2. It is to say this variation, this little motion on the surface, we're here on the surface, this little motion that you decided to call dx, which is arbitrary, may correspond in the parameter space to some arbitrary thing with some d psi 1 and d psi 2. So I must do the x d psi 1, d psi 1, the x d psi 2, d psi 2. That's why I wrote it like this. Now, we are Euclidean space here. We're doing surfaces. So we say the distance, ds squared, is just dx dx. So we do this, and we get what? The x vector d psi I, for the first one, times a d psi I. Now, for the second vector, I should use a different label. So you have d dot dx d psi j, d psi j. And here we go. The ds squared is some number, times d psi I, d psi j, which are parameters of the two-dimensional world. So here you have what you call an induced metric, Gij of psi, d psi I, d psi j. So the induced metric, Gij of psi, is given by the x vector dotted d psi I, d psi j. This is the so-called induced metric. Okay. So why does that help us? Well, it helps us because actually, if you think about it, this thing over here, the area, we can write it as, what is dx d psi 1, dx d psi 1? Well, that's just what we call G11. This is G22. And this term is G12 squared, d psi 1, d psi 2. So this is nothing else but square root of the determinant of G times d psi 1, d psi 2. And the area is therefore, we write it square root of G, like this, d psi 1, d psi 2. And G is, by definition, the determinant of Gij of psi. Let's move these things up. So we gained something. We've written it in a nice way, the area element. Now, how about this reparameterization invariance? Why do I care about reparameterization invariance? You'll say, well, it's some sort of formal trick, and we shouldn't care about it. Well, our life depends on it, actually, in a very important way. We have arbitrary parameters that we can choose. They're very general, and you should check that your firmness are reparameterization invariant because you don't believe that the area of that surface depends on how you parameterize it. So somehow the math should show you that. And if the math doesn't show you that, you're not using the right math. You should strive. So if you had stopped with the dA up there, that would have been a bad place to stop. Here is a much better place to stop, although we're not quite done. Let's try to get done with this now. Now, the fact that this length of this vector, the x vector over there, the length of this dx vector is independent of any parameter is the statement that if you take any ds squared as gij of psi d psi I d psi j, or you take a new set of parameters psi tilde d psi tilde I d psi tilde j, this must be true. For any given thing that you're looking at, you must have the same length. So this is how metrics should transform. This is something you've learned, actually, in general relativity. I'm pretty sure this is something that was written for you. So from here, you obtain, look, what do you do here? You use the chain rule, and you say G tilde ij of psi tilde d psi I tilde. No, I'm going to do this. I'm going to use P and Q here. P and Q. P d psi tilde Q. So I just labeled ij, pq, pq, and used chain rule d psi I, d psi j, d psi I, d psi j. So I can compare these two sides. And then I obtain that the way these things should transform is that gij of psi must be equal to gpq of psi tilde d psi tilde p d psi I d psi tilde q d psi j. This is how a metric transforms, something that you have seen in general relativity. The thing is that, in fact, string theory really begins as general relativity on a two-dimensional surface. And sometime later, it becomes a theory of particles in space-time. But the math, it's all about surfaces and general relativity on the surface. So here comes a little exercise for you. You can now show, exercise, that this formula d psi 1, d psi 2, square root of g, is equal to d psi 1 tilde, d psi 2 tilde, square root of g tilde. So you'll need to use the determinants. You know, basically, if you remember a little of your chain rules, the way this thing transforms is with the Jacobian of the transformation between psi and psi tilde. So it's the determinant of d psi with respect to d psi tilde. And here, when you take determinants for those square roots, you get the determinant of this is the determinant of that times the determinant of this product, which is, again, the same Jacobian. So this thing is invariant. And this is the best mathematicians do in general relativity. They say that the d4x square root of minus g is a generally reparametrization invariant, coordinate invariant measure. So that's it. At this moment, once you recognize that this has this formula, this is the best you can do. And the proof of reparametrization invariance involves one Jacobian and another Jacobian from here canceling each other. It's a simple calculation now. It's 3-4 lines, and you should do it. And so people, when they see this, they say this is manifestly reparameterization invariant, period. So we got a formula for this thing. So now we need to do it for the string. So let me move on to the string. So what happens now? Let's see. Let's try to guess what we have to do. So now we're going to have a space-time surface. So you're going to have x mu, and we're going to call the first parameter tau and the second parameter sigma. This sometimes will be called psi1 and psi2 when we want to be general, but tau and sigma. And here we have, say, sigma and tau. And here is this world of things. And here is space-time with x0 here, x1, x2. And this string is moving in here, tracing a surface. At any given time, you just see one string. But as time flows, you see lots of strings generating the whole surface. This is the surface we have to worry about, this surface in space-time. Yes?
When you do this, the surface element, is it just you find a volume form on the two dimensions?
Yeah.
But, I mean, when you finally do the integration, well, is there some problem of the orientation of the?
No, you know, I'm not sure you're worried about maybe a global problem if you have an orientation in this surface, or a surface is non-orientable or something like that. You know, these are issues of signs that if you're careful mathematically, you can always resolve. You know, when you have dig psi1, dig psi2, this is a notation for something that in mathematics is more like dig psi1, wedge, dig psi2. And you have to be a little careful with those.
I'm afraid because the surface might be non-orientable, so.
You can't put an integration measure on it. It's not orientable.
You certainly can find the area of a non-orientable surface. If you have a Mobius strip, you can integrate and find the area. There's no problem.
There's something different.
Well, you might have an issue of a sign, but you know what the area is. There's no problem.
Yeah, small element, but when you do the integrate out.
You know, take the Mobius strip, cut it, calculate the area, and glue it back. There's really no problem in calculating the area of a non-orientable surface. No real problem. You have to maybe do some little, cut it, calculate, glue it back, but it's just not a problem. And string theory uses non-orientable surfaces, so I couldn't use the cheap answer and say, oh, let's not worry about them, because they don't appear. String theory uses non-orientable surfaces. So you have to be able to calculate their areas. Okay, so what are we going to think about. If we have open strings, we're going to have sigma going from 0 to some value sigma 1. And we're going to call this possible value sigma star. What else do we want to figure out about this? So if we have an open string, these are going to be the endpoints of the open string. Sigma equals 0 and sigma equals sigma 1. I want to mention to you one thing that should be relatively clear. The endpoints of the open string have fixed sigma, either 0 or sigma 1. So the trajectories of the endpoints of the open string are parameterized just by tau. So look, the open string may be a funny thing, but if it's an open thing, it has two endpoints, which is like two particles. And each one will be like parameterized by tau. The simplicity of open string theory is that really the endpoints are like particles, and you can track them. The fact of the thing that makes open string theory or string theory subtle is that you can track the endpoint, but you cannot track the points in the middle. You will not be able to say where, if you have a string at this time and a string at a later time here, you can't tell that this point went to this one and this went to this one. But there will be no way to tell where this point went to. It could have gone here, 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 here. Now that's very strange. In a normal, ordinary string, you would say, paint the string, and you know where everything goes. But here in the relativistic string, this is very elusive. You really can't tell. In fact, where it went is a matter of a gauge choice. Why? Because parametrization invariance means that you can parameterize this however you want. You can call this sigma equal 1/3, and then you say, oh, it goes to sigma equal 1/3 here. That's natural. But now you can reparameterize this string without changing the action, and you don't know where it went. So actually, there's something very subtle about this relativistic string, which you cannot track where the points in the middle go. It's the main thing that is different in a relativistic string from a non-relativistic string. It's a fascinating property. But the endpoints can be tracked. So the endpoints are parameterized by tau. So you will have, for example, the x mu d tau, tau sigma star. So you're looking at an endpoint. It's parameterized by tau. Then this thing, in general, is non-zero. Because you have to have a parameterization of things. And in particular, if you put mu equals 0, it's definitely non-zero. The other ones, the spatial ones, if the endpoint of the string was not moving, that could happen. But dx0 with respect to tau must vary for this endpoint. Because this endpoint is like a particle, and that's the time for the particle. And the time for the particle is always flowing. So this thing is different from 0. Yes?
But related to that, so if we have an actual string, a physical string, a shoestring or something, because we live in a relativistic world, that is a relativistic string.
That's right.
But I think I can track where points go in that case. So how does that?
Well, let's see. That's an interesting question. A normal string. No, I'm sorry. I think. I think this is the answer. However, the normal string that you have is a relativistic string because the world obeys special relativity. But the string that we're going to be talking about is a peculiar kind of string. It's not going to be, here is the catch. So see, we're moving ahead of ourselves. But in a normal string, you have T naught and mu naught. This tension and mass per unit length. What will happen in our relativistic string is that you will have a T naught that you can adjust, but in some sense there's no rest mass, no mu zero. So mu zero is actually T naught over some power of C that I have it somewhere here. C squared. In a relativistic string. So a relativistic string is peculiar in that the mass density arises from the tension. That's another thing conceptually very different from the relativistic string that we are writing. So this relativistic string we're going to write now, we're going to try to write now, is called a massless relativistic string because it doesn't have a mass by itself. Its mass comes from the tension. So this normal string that we have in the real world is not quite this string. And people try to write a relativistic version of this string with arbitrary 2 parameters, and it turns out to be very difficult. And you cannot make sense of it quantum mechanically, so people eventually abandon this. But so our relativistic string is really different from the relativistic version of a normal string. Okay, so I think I got the answer right. Okay, so what happens here? All right. Well, you know, we're going to try to write an area functional, and the inspiration should be clear from there. The area is equal to this thing over there. And we had dot products, and now we should use the relativistic products so that this will be relativistically invariant. So we could try to say the following. The area is equal to d tau d sigma, these are the 2 parameters, and the square root of dx mu d tau, dx mu d tau, dx nu d sigma, dx nu d sigma, minus dx mu d tau, dx mu d sigma squared. Look, we've done just the analog of that thing where psi 1 was called tau, psi 2 was called sigma, and instead of normal products, Euclidean products, we've done relativistic products. Now, we can try to see if this makes sense. And actually, it's close to making sense, but not perfect sense so far. So let's see how that happens. For that, I will just still write it in a little clearer language. There's no need to put all these indices like that. You can write dx d tau dot dx d tau. And this dot is the relativistic dot. We use vectors there and dots, but there need not be confused a relativistic product like this. We can write the x d sigma dotted with the x d sigma. Forget the mu's and nu's. And here, the x d tau dotted with the x d sigma. You can still simplify this writing, and we want to simplify writing because this is a little messy. So the x d tau, we'll call it x dot, and the x d tau, we'll write the x dot squared. X prime here, the x d sigma, and squared, minus x dot dot x prime squared. can you keep track of this notation? It's not a big deal, but so what is x dot square is the x d tau relativistically dotted with the x d tau and all these things here. And I should put question marks here because I have one little problem unless I could be a little sloppy and say, okay, everything must be right, but there's a potential problem. Look at that square root there. It's actually, look at that formula over there, top blackboard there. Why is that right-hand side positive?
By the Cauchy-Schwarz inequality?
Sorry, by which?
By the Cauchy-Schwarz inequality?
Exactly. Schwarz inequality shows that the dot product is less of value than the norms multiplied. So that's positive, which is good for the square root. Are we sure this is positive here? All these signs could have ruined things, or maybe the Schwarz inequality still saves you. Yes?
The time lag vectors, it should be negative.
That's right. This thing actually has the wrong sign, as we will see now. So we should take it the other way around. What happens there is that in a Euclidean space, the Schwarz inequality works well, but this metric that we're talking about, you see, you have a metric in 4 dimensions, and it has 1 negative sign and 3 positive. Now you got an induced metric on the surface, and you can ask, what is that induced metric on the surface look like? Does it have 1 positive, 1 negative, 2 positive? Maybe there may be surfaces with 2 positives inside the space. And here's the main concept that happens here, is that the intuition of the space-time surface is a very fabulous intuition. If you have a space-time surface here, and you have a point, this is the surface. And remember, this is a mathematical construct. If you have a string, it's a string here, there's no surface. The surface is in space-time. Around this point, there's a tangent space. It's a 2-dimensional tangent space because it's a surface. So there's 2 basis vectors maybe here that we could use. And these 2 basis vectors, what is the key idea? The key idea is that there must be at least 1 space-like vector and 1 time-like vector among the tangent space at this point. 1 time-like and 1 space-like. Why is that? Think of yourself as a string. Take a picture of it at any given time. Consider that point on the string, and you have the string here. Consider a little vector along the string. That's a space-like vector, because it's all those points are at the same time, and that's a real displacement. So that's a space-like vector on this surface. You draw the surface at some given time and take a little vector. That must be it. But this point on the string is moving. It's going to move. So in some sense, every point is going to act a little like a particle that is going to move. And therefore, there must be at least 1 time-like vector. This is the main thing you have to understand about a string and a surface in space-time. There must be a space-like vector, and there must be a time-like vector. Now, I said that the points inside the string, you cannot know where they go, so you may feel a little unhappy. But look what's happening here. In general, what has to happen, so suppose this is a t equals 0, and this is a t equals 0, 0, 0, 0.1. And suppose that in this time, light could have moved up to 1 centimeter. we will learn that the endpoints of the open string move with the speed of light. So here is 1 centimeter, and here is 1 centimeter. Now, here is the rest of the string. Take this point and consider the 1 centimeter and draw a circle of 1 centimeter. So you don't know where this point went, but it could have gone any of these places that it can move less than the speed of light. But it should be able to reach here. If this string would have looked like that, and you look at 1 centimeter and you cannot reach, that's not physical. Is that right? So there must be some point that this initial point can reach a little later. So at this point, there are a lot of time-like vectors. And there's many space-like vectors, but the time-like vectors are these ones because they correspond to possible motions. So the world sheet at any point must have one space-like vector, at least, and one time-like vector. And that's the physical condition. Even though you don't know where points go, that should happen. So here is this is the last thing I'm going to do because I want to finish that. Here is a claim for a surface with one time-like, with a time-like vector, a time-like vector. There are many, and a space-like vector. Then x dot x prime squared minus x dot squared x prime squared is greater than 0. So it's the opposite sign over there. So here. And I was going to do the proof, but I think I'll spare you the proof. Another way of thinking about this is that in a space with one time-like direction and a two-dimensional space with one time-like direction and one space-like direction, the Cauchy inequality is actually completely reversed. The argument, this claim, is proven in the text. It's a nice proof. I think it's a very important concept because this is what really differentiates a surface in space from a surface in space-time. It's really the concept of having one time-like direction and one space-like direction. Now, suppose you would have found that here it's like that, and barely one point touches. Then you know that this point can only have gone here, and it couldn't have gone anywhere else, and it's moving with the speed of light. And that will correspond to the case when this whole thing under the square root is exactly 0. So when this is exactly 0, there is one time-like vector and many space-like vectors. Only one, and you're moving with the speed of light. So what have we gained? Now we know the right sign, so we can finally conclude this lecture with the Nambu Goto action. D tau from tau I to tau final, sigma from 0 to sigma 1, d sigma, and the square root of x dot x prime squared minus x dot squared x prime squared. This is the area element integrated. So now this is the action. Remember, for the point particle, you had ds and you had to put minus mc. So you now need to do a little bit of unit chasing to, as Mark said, units and dimensions are the most important tool you have. As to what you should put here, the sign is the same sign. And the things that show up is one parameter only is necessary, and you can call it a tension. And you need to put a C here. We'll discuss some of that later, but that is our final action. It's called the Nambu Goto action. And is the action for the motion of a relativistic string. This is history reversed in some sense. The way string theory was discovered, people found all these interesting S-matrix elements for tachyons and other particles, and there seemed to be infinite number of excitations. And Nambu and Goto said, oh, how about a string? And they wrote something like that. And it took years before anybody could quantize this to see that the quantum mechanics of this action gives, in fact, rise to all these particles and all these things. So this is what we're going to be doing in this class, not today, of course, but we finally have the action that we're going to need. If you're going to do a little bit of studying, what you should study today is this proof, and just feel comfortable with these things so that we'll practice with them quite a lot tomorrow. All right, done for today. If you have any questions.